Okay, so question 7 for the third part of forces in motion. So we've got which of these quantities is a scalar? So a scalar is something that only has, we'll put my pen on, only has magnitude, no direction. Whereas a vector has magnitude and a direction, so we'd represent it with an arrow. Now, obviously, you can accelerate upwards, downwards, left to right, and it makes a difference which way you're going. So that would be a vector. Force, again, you can draw arrows for forces. You can have a force like we have here. We've got a force going to the left, and we've got a force going to the right. So force is a vector. Velocity as well. It would make a difference to you if that van was traveling this way or this way, one forward or backwards. Velocity also is a vector. Energy is the only one where there isn't a direction. You can't have plus 10 joules or minus 10 joules or something like that. The amount of energy you've got is the amount of energy you've got available. There's only the size of it. I've got more energy or less energy. The diagram shows the horizontal forces acting on a van at a particular instant as it accelerates. So we've got air resistance pulling it back, and we've got driving force pushing it forwards. Probably more to say the air resistance pushing it back. Calculate the resultant horizontal force acting on the van. Well, we always add forces together, but we have to be careful because force is a vector, which means you can have positive forces and negative forces. So it's quite normal to consider forces going this way to be positive, and therefore forces going this way to be negative. So in this case here, I've got my driving force there, which is 8,000, which has got a plus sign there. I'm going to add to that my air resistance there, which is a minus 1,250. And I'm sure we're aware that plus and a minus can make some minus. So we end up with our answer of 6,750. And that's a positive value. So that's 6,750 newtons. And a positive value means it's going to the right. Okay. State the equation linking resultant force, mass, and acceleration. Well, we should remember that resultant force symbol is F, which doesn't stand for force, it stands for resultant force, equals mass times acceleration. There. So the mass of the van is 2,500 kilograms. Calculate the acceleration of the van and give the unit. So the first thing I need to do is I need to have acceleration, and I've got force as my subject there, so I need to rearrange it. To rearrange it, I'm going to divide by m. So divide both sides by m, I get F over m equals A, which means my force, well, this one here stands for resultant force. I just calculated my resultant force. So whatever I've got there, 6,750 newtons. That's going to go there. And then it says my mass, and my mass is 2,500 kilograms. Okay, now when I do that, I'll get my calculator working. Over here, 6,750 divided by 2,500, I get 2.7. Now, here the unit is interesting. Now, using standard ways we do in every other circumstance, we've got newtons per kilogram is what we're going to use. But for acceleration, you need to remember that the unit we use is meters per second squared. That's the ideal one to do that when talking about acceleration. Now the graph shows how the velocity and time, lost my page, of the van changes over time. Explain the shape of your graph. Use ideas about forces in your answer. Well, the first thing I'm going to notice, there's a few things to explain in this graph. The shape changes. So the first thing I notice is it's between sort of there and there, it's a straight line. And then from around here it curves. And it's curving till about here. And then it's a horizontal straight line. So in terms of velocity, the gradient of a velocity time graph is our acceleration. So our steepest acceleration is along that path there. And then here, our velocity is still increasing, but my gradient is getting less as I follow that curve. And then over here, my gradient is 0. So that means we're doing something new there as well. So the first thing I want to do is explain this first region here. So that's that shape there. So here we've got initially between what we've got there, between 0 and they might even go all the way to 20 here, but I'm sort of more attuned to around about 18 or so there. Between 0 and I'm going to go 16. Between 0 and 16 seconds, we've got constant acceleration. Okay, with our velocity increasing. Okay, and we've got constant acceleration due to the resultant force being a constant. Now, between after 16 seconds till about 50 seconds, between 16 seconds and 50 seconds, we've got the resultant force must be decreasing. We know that because acceleration is decreasing. So as the acceleration is decreasing, we can see that because the gradient is getting shallower or less steep. Okay, so how am I going to explain that? Well, as we're getting faster, the velocity is getting bigger, which means that the air resistance is getting bigger. So here we've got the air resistance is increasing as velocity increases. So therefore, resultant force is getting less. Okay. Then we've got from 50. Well, and the reason it's getting less here because also the driving force is obviously a constant. Oh, pen went weird. Constant. Okay, but then between 50 and 80, or rather after 50 seconds, the driving force equals the drag or the air resistance. So therefore, no resultant force, therefore no acceleration. And that's why we got that horizontal line over there.